Good afternoon. My name is Rachel Friedman, and I'm the Communications Manager for John Jay's Office for the Advancement of Research. I want to thank you all very much for joining us. Every semester, OAR hosts a series of book talks with authors of notable books that are of interest and import to our college community. Today, we are very pleased to have the opportunity to hear from Dr. David Munns, who's going to be speaking about his book, Far Beyond the Moon, A History of Life Support Systems in the Space Age, which was published last year by the University of Pittsburgh Press. To give a proper introduction of David, please welcome Dr. Allison, a professor of history at John Jay College.
Thank you very much. And thank you everyone for taking the time to listen to David today. I think this is such an interesting book and such a fascinating, in many ways, defining modern topic. And so I am happy to introduce someone who in 1999 said he would marry the next person who handed him a pencil. And I was that person, but we are not married. He has more pencils now in our office than anyone in the world. And I was very, very proud to be the person who brought him to this college as his chairperson. He has worked throughout the world, including being a writing fellow at the Rachel Carson Center in Munich, most recently 2017. He was a lecturer at Imperial College London. He worked for 6 years at Drexel College, and before that at Johns Hopkins. He has published a series of books that in many ways, I think, define and interrogate systems of thought and institutional relationships between science and technology. In our field, we call this the big tech stuff. But actually, I think what he's doing is not just talking about technology, but human systems relationships to technology and how those relationships then inform the questions that we ask about the natural world and in fact produce new scientific communities as a result. His new book is, well, the book that you're going to be hearing about today is about life support systems in the space age. It was released, of course, last year, Pittsburgh University Press, and he has a forthcoming book, which is on nuclear reactors and the emergence of the profession of nuclear engineers. It's my great pleasure to welcome him here today and to welcome all of you to this talk. I look forward to hearing it myself. Have a great time.
Thank you all for joining. As is customary, I shall start a slideshow. I have a slideshow to talk through the kinds of things that I'm doing. So I'll just start that up. Our new way of looking at the world through Zoom and slideshows. And then slideshow, play from the start. And with a bit of luck, you should now be seeing the title slide. So thank you all. I want to introduce you today to a very strange and somewhat unfamiliar world, even though it is actually very mundane, which is a world of space sanitation engineering and a world of recycling systems and a world of astronauts and how do you go to the bathroom in space. The title is Far Beyond the Moon, which we will see was always the goal of space programs, really from the beginning, was that the moon was only ever going to be a stepping stone to the wider world. But in fact, that's basically as far as we've gotten thus far. The subtitle is actually the title I was not allowed to have for the book, which is an excremental history of the space age. This was considered far too much fun. And my German co-author and my publisher decided that no, we couldn't have that much fun. But you will see why I tried to sort of go down the line, because it is an excremental history, which means something. This journey has been quite exciting since I've been at John Jay College. This is the third book I've now published. The first was on the history of the radio astronomy community, which was really the history of a community which took up a new way of seeing the universe by listening to the universe through radio telescopes. The second book, which was published 4 years later, was called Engineering the Environment, and it took up the challenge of a new way of understanding the biological world through controlled environment engineering, and the ways in which they were attempting to engineer the control of climates in order to test biological organisms living and growing. It was in fact from this book that this project generated. During the later stages of the book, I applied to a conference in Munich. I was invited over because my future co-author had never heard of the device that I was talking about in that book, which was called a Phytotron. And over the course of the talk, which she thought was a little strange, she actually then goes, well, I've never heard of a Phytotron, but have you ever heard of the Algaetron? And I'm going, I've never heard of the Algaetron. That sounds very fascinating. Well, you know, we should work on this. It was a device that you shall hear more about. And so this was the genesis for the third book. I had the opportunity to go to the Rachel Carson Center in Munich for a very marvelous 6 months, as well as being well supported by my then chair, Allison, as well as our institution at John Jay and CUNY, which really also helped bring this book into fruition. So what Kärin and I discovered was that the Algaetron was not, as we first anticipated, a device which was designed to feed the world through the production of algae and the production of proteins from algae, but was in fact a sanitation device. The Algaetron, seen here with its creator, was William Oswald, who was a member of the Sanitary Engineering Department at the University of California, Berkeley, was a device that he came up with his co-developer Clarence Golica in the late 1950s, by which the waste from an organism, in his particular case there, if you might be able to see on the screen, what he's indicating with the pen he's holding in his hand are 2 white mice, which are living just above the mesh section of the Algaetron. The mice produce waste. They produce carbon dioxide. They produce fluids, feces, urine. That falls through the mesh into the opaque solution below, which is an algae solution suspended in water, lit by lamps, which the algae absorbs all of those waste products from the mouse. And in fact, the algae itself excretes protein, it excretes oxygen, and absorbs a lot of these things. Thus, the mouse and the algae become 2 parts of a closed organic system, whereby the waste of one becomes the nutrient of the other, and the waste of the other becomes the nutrient of the other. The 2 mice in question lived in this configuration, closed in that environment for over 200 days, which was the most sort of successful that they were in these kinds of ways. For Oswald and Golica, this was a revelation. As the space program ramped up in the late 1950s, the United States locked in the space race with the Soviet Union. One of the key challenges to not only visiting space, but living in space, was the ability to deal with one's waste. As they said very famously at a conference hosted by NASA in 1966 all about assembling artificial environments, is they were shocked that NASA had adopted such startling do-it-yourself processes for the handling of feces, which was a specially constructed glove. As it turns out, this is exactly what the Apollo missions and the Gemini missions went into orbit and then went to the moon with. They went with a plastic glove into which the astronauts would deposit their feces and then store. The problem with humans going into space is, from Oswald's point of view, is that humans excrete a lot of stuff. As they said, they give out urine, perspiration, skin oils, nasal mucus, sputum, saliva, tears, semen. These liquids, which were challenging enough, were also augmented by various gaseous wastes, carbon dioxide, waste vapors, regurgitated gas, and flatus. This was the earthy reality of the space program, a reality we don't often see in History Channel documentaries or coffee table books about the heroic astronauts going into space. No one publicly talked about this stuff, but behind closed doors, within NASA and the Soviet space program, this was not only a hot topic, this was in fact a major scientific and biological problem. The solution, as far as Oswald could work out, and Golika, was to build and was to scale up the Algaetron that they had built in miniature, so that it could become a module to be fitted on the Saturn V rocket. The plan that they had, and this was really as far as they got by about 1965, was that you would have two rotating drums, rotating counterclockwise, because you don't want to put a spin on your space vehicle because it has no downward direction. Then the astronauts themselves would go into this ladder area. They would do their business. This whole talk is nothing but euphemisms. They would do their business, and then it would be processed via the algae solutions. One of the problems here is about energy. Where does the energy come from to allow the algae to do its work? And one solution was for artificial light through the center, but the other, as you might be able to see, was actually that they designed little circular window ports so that you would orient your space vehicle so that one was always pointed towards the sun, and solar radiation would be your primary energy source. This was designed, if anyone is familiar with the design of the Apollo missions, this would be designed to go in between the command module and the lunar excursion module, the LEM, and it would wedge you in there. Of course, for those of you who have watched History Channel documentaries, you know that that never went in there. The command module and the LEM was actually attached to one another, and this biological piece of technological equipment was never deployed in the space program. Among their achievements was not only coming up with these ideas of organic beings locked into recycling waste nutrient cycles with one another, but they also first saw an insight into what has become, in fact, our primary major problem during the era of climate change and the Anthropocene, which is that what does an ecological system look like? How does it function? And what is the role of the human within that? For them, the ecological system that they constructed in the Algaetron was really, as they called it, a miniature version of the grand scale terrestrial ecological system of which we are a part, in that the basic principles of the two systems are the same, the Algaetron and the Earth, only the size and the variety of their constituents matter. And thus NASA, the hard end of the military-industrial complex, an absolutely modernist technological project, is revealed to have discovered something very important, which we often fail to appreciate. What they appreciated was that humans are one part, not even the most important part by any stretch, of a large-scale terrestrial ecosystem of which we are dependent upon the other organisms in that system. Without algae, without trees, without plants, the human organism isn't going to live very long. Bees are probably what's going to kill us all off first. No more bees, it's all over in about 6 months. This is a revelation, and that it comes not from the systems of ecology, that it doesn't come out of systems of environmental thinking, that it actually comes out of a pair of sanitary engineers working for NASA, trying to take humans to another place, is part of the reveal of the book. And they weren't alone. They weren't alone at all. It could very well be that it was just two obscure American sanitary engineers working out of Berkeley, which is always a little strange. That could be fun, but it's not. every part of the military industrial complex had a project just like this. One of the more entertaining, for which there is actually very good illustrations, which we used in the book, was actually at Boeing. Boeing Aerospace, a major contractor for NASA, and is still a major contractor for NASA, investigated not only the image on the screen on your left, not only investigated the dealing with waste products, particularly feces, through an algae sludge solution, which is really how feces are dealt with even in waste treatment centers, but then in a rather remarkable public affairs coup, actually the head of Boeing Aerospace took that algae that is produced from feces, actually got his assistant or wife, it's actually unclear who she is, to bake algae cupcakes, and then very famously ate the cupcake for the cameras in a major publicity photo. He then, of course, though they didn't photograph this, presumably excreted the waste product of this algae cupcake and actually redeposited it back in his own solution. And so this kind of testing, which is very famous in the sciences, this sort of self-testing is one of those things. Indeed, there is a story that Kärin and I heard from one of William Oswald's own collaborators late in life, that in fact, William Oswald actually took up this project and actually made his graduating seniors eat cupcakes, which he claimed were made from his own algae waste as well. That was the last thing you had to do to graduate from Berkeley. And so this was sort of the introduction to the book as we built it. The book then really took as its introduction, reconsidering the space program from the bottom up, considering not when astronauts and glorious rockets and all those images of people in Florida in sunglasses with perfect perms looking up at the ascending astronaut rocketing into space, but instead looking much more at the earthy, much more mundane, much more down-to-earth problems of what does it mean to solve a waste management problem? A problem that is essentially ignored or certainly pushed to one side in many areas of society. As we argued in chapter 1, the United States and the Soviet Union were locked in a race not only to the moon, but in fact to beyond the moon. They always had in mind getting into Mars, going out to the outer planets, and indeed, the speculation was always rife, even from the beginning, to go much further than that. We then use the Algaetron versus the Fecal Bag, the actual bag that astronauts actually used, as a nice case study about how technologies get decided upon. Why NASA and the space program did not use an organic system, an organic biotechnology system like the Algaetron, but instead used, quite frankly, a plastic bag with a piece of elastotape on top. We then had an important comparative chapter with the Soviet People's Planet ship. The Soviet Union had a very substantial project into the life sciences in space, and they built what they called planet ships. They were model enclosed environments on Earth where their cosmonauts would stay in for 6 months, or even in several experiments, an entire year, locked in a room with their own nutrients and waste and air and plants that they grew inside, and that's what they lived on inside these environments. We then moved on into the 1980s, when NASA returned to these kinds of projects when they were trying to build Space Station Freedom, which was the major Reagan era idea. Space Station Freedom never went up, but most of those components got morphed into what is now called the International Space Station. And finally, we concluded with a project that a lot of people have heard about, but we argued was not correctly situated, the Biosphere II project, which is outside of Tucson in Arizona, which was itself also an enclosed environment that 8 biospherians attempted to live in, very much in the style of these space farers which had gone before them, as we suggested. So this sort of, the book that we wrote then was in many ways an excremental history of the space age. And what does that mean? There is ways of telling histories about sciences and technologies, which are, of course, very triumphant. We all succeeded and we all did this. Very famously, if you're Watson and Crick, you're appearing next to the model of the structure of DNA. Look at this thing that we have discovered. There is another way to tell the history of science, because that way is actually very triumphalist and really hides more than it reveals. When you start talking about the history of shit, or your Piero Manzoni, and you're actually canning your own shit and putting it on display, you're actually giving it to major museums everywhere in the world. You're selling it for its equivalent in gold weight. When you're talking about waste in other places, you start to reveal things about people's worldviews and their thoughts and ideals and how they understand the world, which you would think would be more hidden, but in fact reveal more about the world. We really drew this from a pair of very prominent sources. One was a fantastic book by Iko Sinawa, which was all about waste in consuming post-war Japan. And as Sinawa argued, that the lived reality of people in the past, as well as how historians have talked about that past, is really more deeply informed by looking at the moments about what to keep and dispose of. What we choose to keep and what we choose to dispose of has a remarkable capacity to reveal what is valuable and what is meaningful. So when you're dealing with societies that are about consumption or about material objects, what they choose to deal with, how they choose to dispose of waste becomes a major thing. And Japan by the 1970s really faced this problem. And they, unlike most Western countries, which sort of push waste out, very famously, we still export most of our recycling to other places, the Japanese embrace the idea that waste should be kept closer to home and you should embrace your own waste, because in fact, there really is no such thing as waste. Dominic Lepore, in a more philosophical treatise, talked explicitly about the history of shit, but again, made this kind of way. That shit is something that most people reject, but occasionally in various places has been understood as a valuable commodity that needs to be reintegrated with the lived experience of people's world. And so you actually learn more about the experience of people in the past by looking at their shit rather than looking at that which they celebrate and that which they display. This appears to resonate very strongly with the space program, is that while every coffee table book that we've all looked at on the history of the space program will give you thousands of photos of heroic astronauts and parading out, and of course the classic, the right stuff, the 7 astronauts walking down the gangway, which of course has been deployed in everywhere from Monsters, Inc. To The Incredibles. It is such a powerful image about what the space program is. It hides that which was actually important. As Scott Kelly, who actually up until last week was the person who had spent the longest in space, he has now just been done by the guy who just came back. Scott Kelly, in his memoir, published just in 2017, told his readers that the toilet on the International Space Station is, quote, the most important piece of equipment to master. If the toilet breaks down, the mission is almost invariably scrapped, because waste cannot be allowed to accumulate, it cannot be allowed to gather, it has to be part and parcel of a recycling system. The image on the right is the current configuration from the Mir toilet, which is actually the female configuration, which was used on Space Station Mir by the Soviet Union up until the late 1980s, which is one of the artifacts at the National Air and Space Museum. The image on the right is the current International Space Station toilet. And I leave this as an exercise for the audience, as I always do for my students, to go, how does that work? Because you need to know how the toilet works, which is actually very fun. Happy to get into the Q&A, but it really is more fun if you try and figure it out by yourself. In contrast, the famed fecal bag, which really went up with every astronaut from the earliest Mercury missions through the Gemini missions of the 1960s, the Apollo missions, and even into Skylab and the early space shuttle, they went up with what is called the fecal bag. The fecal bag, and this is again from the National Air and Space Museum, one of their more popular artifacts, as it turns out, though they don't like to celebrate it. I keep telling the curators they should move it to the front of the museum. This is an unused, importantly, it's unused fecal bag that went with Apollo 11 all the way to the moon and all the way back again. And it's a very well-traveled bag. The patch, which is really a dark green but looks sort of black in this image, is actually an anti-biological agent, so that after you have deposited your feces inside the bag, you actually have to crack the antibacterial agent open, put that in with your feces, seal the bag, and then actually massage it, very famously, to make sure that all of the organisms which actually live in feces are rendered biologically neutral. This was part of a very major project by the United States in particular to keep space biologically neutral. As Mike Mullane, who was a space shuttle astronaut, admitted that having to be toilet trained, even though he is this doyen of American white masculinity, to having to be toilet trained and fitted for a urine condom took a lot of the glamour out of being an astronaut. And this was this irony of this paradox of the sort of the most celebrated figures in a society having to deal with the least talked about elements of that society is really what makes the book there. The American space program itself took care of this kind of problem. One person said back in 1964, the problem of waste handling was eliminated by eliminating elimination. There is a reason that the United States only goes into space for a very long time, for very short periods of time, is that if you simply go into space for only a couple of hours or a couple of weeks, or even, or in the case of Apollo 11, 11 days, you can actually take care of the waste problem by simply storing it, which is actually what they did. They stored all of their waste and they simply brought it back. Only once you cross the threshold, and that threshold is about a month, once you get over a month, the cost of launching water and food, which simply gets, quite frankly, pissed and shitted out, that then you have to store, is so vast that you can no longer justify not recycling your own waste. This leads to an immediate question of how long can we spend on the planet Earth simply consuming and only doing without the requisite recycling of waste. And so NASA came up with these kinds of diagrams. They came up with a diagram that if you wanted to live in space on a space station or a lunar base or a Mars base, what you needed was a crew. You needed a biomass production. You need to grow food. You needed some kind of food processing. Plants are not themselves edible without some kind of processing. But what you also needed was a waste processing, which, and we dwelt on this, the size of the crew, the size of the biomass production, and the size of the waste production are all equivalent. They are actually equivalent in size and somewhat equivalent in complexity. Indeed, the crew is actually somewhat the least complex part of this equation. It's the waste processing and the production of food that is the most significant parts. Now imagine your house. Your toilet and its recycling area should be as large and more complex as as your kitchen and your living area and the pieces that you use. But instead it's not, which tells you about what we value in these kinds of ways. And this is the challenge that the space program has been going on for years. An early diagram from the 1960s, the position of the astronaut in context of its environment, these recycling systems where nutrients and wastes are treated and processed, taken out and come back, like the current configuration of the International Space Station water and water system, is this as well. The astronaut, the person themselves, is a much smaller component than we imagine in the idea. And this is exactly what Boeing Aerospace again discovered as early as 1963. What when they first built their first completely closed environment as a test module, they built a waste disposal system which collected and processed all body waste from the interior cabin. It collected all body condensation and sink drainage. They even had a closed circuit shower, they told everyone. The experiment was supposed to last for 30 days. 4 guys went in and they lasted 5 days. They were evacuated after the 5th day. By day 2, they were starting to perspire. By day 3, they were throwing up. There was yellow leakage coming from the new plastics that they had built it out of, coming out of the seams. The actual plastics themselves were giving off gases which were never effectively identified. And indeed, the environment itself that the astronauts were producing were in fact poisoning them. We live in an idea that our own wastes will poison us unless they are effectively recycled. And so Boeing went back to the drawing board. They locked their head of biotechnology and astronautics, Romney Lowry. He went inside a chamber like this one, which actually supported him for a full day, breathing the oxygen produced by algae, which is in the ribs around the top. With the algae itself is living from his own breathed out carbon dioxide. He is sealed in this. They had to break down the environment into its component pieces and try and figure out how these things go. General Dynamics, which went along, complained to NASA in 1965 that really the problem of going into space was actually not getting into space or even coming back, though they're very tricky problems. The trick was that no one knew how the food waste loop was actually constructed. You couldn't engineer how food and waste were constructed with one another. And indeed, General Dynamics, which 2 years later developed the Tomahawk Missile, complained to NASA that urine and feces are prime examples of poorly defined substances. The problem wasn't living in space. The problem was nobody knew what was in urine and feces from an aerospace engineer's point of view. And so no one knew how you could return those products, those waste products, as nutrients. And so like this is great. The sort of that's the Tomahawk Missile also hanging in the National Air and Space Museum. And I keep telling the curators to put the fecal bag directly underneath, because one's hard and the other is actually really not. And so this then was what was happening as NASA was developing plans for its space station, which really came on in 1966, which was to really close all the loops to provide a, as they called it, self-sustaining ecology. And this is really the major point, actually. The major point is that before an ecological vision took root in the 1970s, before the first Earth Day of 1970, before we get the modern environmental movement, NASA and the guys who invented the Tomahawk Missile have discovered that the challenge is about providing a self-sustaining ecology. And the challenge is to both miniaturize it for space vehicles, but also what does that look like at the scale of the Earth? And this is the major insight, which regrettably was actually really never taken up by anybody. NASA discovered all this stuff. They discovered all this stuff in the 60s. It's all publicly available. And yet it is entirely set aside. And so what we have come across is that now in the International Space Station in the 2000s and the 2010s and 2020s is we're almost back to ground zero again. The first plants, lettuce, I think it's a type of arugula. The first plants are now only just being grown on the International Space Station. We're now having to reconstruct all of this ecological knowledge, which they were starting to have in the 1960s, but which was largely swept aside in the rejection of a lot of those things by the 1970s, which is rather a shame. As Dan Barter told us, this is him as a very young graduate student in the 1980s. He himself is sealed with, for those of us who remember Anthony Carpi, I think you'll remember this, he's wearing a Walkman and a little calculator wristwatch. It's very fun. He's locked in a sealed environment with a bunk, his Walkman, and growing wheat plants so that he was able to do these new experiments when they were gearing up for the space done in the 1980s. And this is really what they had. And one of the problems here is that the understanding of biology as a science was very much challenged by this meeting of aerospace engineers, rocket engineers, environmental engineers, life scientists, veterinarians, plant physiologists, and even the occasional ecologist, who, as it turns out, aren't very useful. They're meeting in the production of a closed environment in the space program. And what they discover, and this was sort of one of those great quotes if you're a historian of science, which is that biology is not this way, complained the engineers. Where are the firm variables? Everything was a complex system embedded within complex systems. Everything was a feedback loop embedded within feedback loops. And so what you got was actually a very interesting example about the ways in which science itself and the sciences are understood and historically placed, how they grow, what kind of knowledge they legitimate, and how their practices operate, because the plant physiologists had to work with the environmental engineers in order to design these kinds of systems. Okay, Allison, how am I doing for time? Okay, very good, very good. So I shall wrap up very well. There is a fun other example, the book we could have written but we didn't, which was all about the psychological processes. This is really about physiology. And again, the same kind of story seemed to emerge. If you want to test how people are going to survive in tight environments, how do you do that? One experiment was actually that the Soviets, again, who were rather more interesting about this kind of thing than the Americans, booked themselves on the Ra-2 experiment, which those of us of a certain age will remember was the rafts that sailed across the Atlantic from North Africa to the Americas in a test to see whether or not that could be done. Though this is actually a photo of the Kon-Tiki, which just photographs better. And finally, we ended up the final chapter with Biosphere II, which was the most modern effort at a much larger scale than anything NASA had ever attempted to seal 8 people inside a closed environment, which they did for 2 years. And I can get into the Biosphere II because normally we have this. The key lesson of the book that we came up with was that the transformation which we are currently undergoing in the modern age, which is about imagining humans as so much smaller than their biosphere that actually their actions don't matter, has been transformed by these kinds of ideas so that humans are now approximately equal to their environment. That it matters a great deal, all of the waste that we keep putting out. That is now doing huge effects on the environment. And as we know from the latest IPCC report, we have a very short window in order to do this. This information was actually really available through the space program, even by the late by the late 1960s. But there is a cultural and social battle as we come to it, because we have to talk about waste. And so in the end, we really relied on things like the reconsideration about what waste even is. Mary Douglas famously observed that waste that dirt is really not anything except disorder. What we consider dirt, we eliminate dirt by eliminating a negative, but it is in fact a positive moment that when we tidy or we clean, we are organizing our environment in these ways. Donna Haraway more recently has more forcefully said that actually, if we are to avert anything in the Anthropocene, we need a hardy soil kind of wisdom if we are to divert disaster even a little bit. We would argue that one of the lessons of the space age and the lessons of looking at it from below is that the hardy soil kind of wisdom is looking at our waste, looking at our shit squarely in the face, and dealing with the kinds of waste that we as a society and we as individuals produce. And with that, I will thank you. I will thank everyone for coming to the talk, and I look forward to any questions that you might have. So I'm going to stop sharing the screen, and then, right. How should we handle the several? I think there are some Q&As as well as some questions in the chat. Allison, what do you think? Should you take them in order?
I don't think I can see the Q&A. I think I can only see the.
Only I can see the Q&A.
Wait, hang on. No, okay. I can. I lied. I'm sorry. I've got it. So from Nancy B. Lewis, my mother, a docent at the Air and Space Museum from the 70s until the early 2000s, would take her tour groups of children into the wing that showed the astronaut spacesuits and explain how they went to the bathroom, which is pretty great. And then might some of the recycling devices and processes you discuss in this talk find utility here on Earth?
Absolutely. Nancy, you're absolutely right. One of the fun facts we discovered reading through all of these astronaut biographies is that every astronaut will tell you the first question they get asked by every child is, how do you go in space? It's the only question children are basically interested in. And so this then is actually a very important question, because it shows the ways in which knowledge is socially constructed. After a certain age, children learn they are socially constructed to just not talk about that kind of thing anymore. Whereas in fact, innocent that they are, this is what they want to go in. And so the kinds of processes that they have is really about, there were many ways to deal with this, because one was about direct recycling of the substance itself. Do you just take urine and feces? Do you reconstruct it? Do you grow soil out of it? Very famously, the novel by Andy Weir and the most recent movie with Matt Damon, he uses his own and his compatriots' physical waste to grow soil from dried earth to create earth. That's dried earth, capital E. He creates earth, small e, which he can actually grow his potatoes in. That in fact, in the novel, makes the claim that NASA has been making for many years, just that our own waste is part of our own life support system. And so this then is when we flush the toilet, when we throw something away, we should be more attuned to the ways in which that is actually what we need to survive. And unless you can sort of see those cycles, what we're doing is we're actually throwing away our own life support systems, which I think is very important. But yes, the astronauts are quite good. And then there's a challenge about what you put on public display at a national museum about waste sanitation systems. I've had a number of discussions, but I would very much like to talk to your mother about these things. Thank you. Thank you very much.
So we have another question from Elizabeth Hovey. Can you tell us what did or didn't work about the Biosphere II?
Oh, absolutely. Thank you, Elizabeth. Yes, no, the Biosphere II is endlessly fascinating. What worked in the Biosphere II, we argued, was the space life support version, their version of controlling their atmospheric contaminants, their version of monitoring all of the components of their environment. What didn't work was a greater understanding about the role of the human in the environment. They themselves only became aware of their own agency within the making of their own environment. Of course, they knew this, but there's one thing to be trapped inside a building where you become far more aware of this kind of thing at really the cutting edge. And it was also about the sort of idealism of ecology not really being very useful about the practicalities of actually controlling an environment and regulating that environment. There is also lots of stuff actually about algae. They didn't know how to use the algae, which was blooming. They didn't know how to use the cockroaches, which were blooming. These are the things we're going to have to live on unless we alter ourselves even a little bit. I'd suggest we all get used to cockroach stew because they're going to do very well about 50 years from now.
We have a question. What would you say is the most promising? And I think the question is really the most promising means of disposal or repurposing waste.
There are a number of solutions to this problem because they are always complex. They're complex systems locked into complex systems. And one of the problems here is about the challenges of what used to be called cybernetics, which is that how do you take a system which is dependent upon itself where it's complex? The energy requirements to deal with waste is very substantial. And so the idea in this early space program was that biological systems, putting waste through algae, putting waste through other plants, higher plants, putting waste through bacteriological, that these were energy systems that could convert waste back into usable forms in a more energy efficient ways. A lot of the stuff that actually goes through is really just, you just break all of the energy, all of the waste apart, and then you just reassemble it as useful things. So carbon dioxide, if you put enough energy into it, it comes out as carbon and oxygen, and you can breathe the oxygen and then you figure out something else to do with the carbon. Other kinds of waste actually organic waste just breaks down this way too. You can simply break it into its molecular components and then just reassemble it as you wish. The problem with that is that there are substantial infrastructures that are required in order to do these things, and suddenly you're multiplying the amount of systems you need instead of an elegant engineering solution, which is, say, what Oswald thought the Algaetron was. It was an elegant engineering system because it directly tied the waste of one organism with the nutrients of another organism, and the waste of that organism with the nutrients of the first organism. That's sort of one-to-one. That's an elegant engineering solution to the problem, which could be easily contained. But biological systems simply don't work this way. They actually require substantial amounts of space. They require substantial amounts of time in order to regulate and work themselves through. This is also a problem with these kinds of things. We want to go into space. We want to go to the moon or Mars. We want to come back again. The current solutions, which are when you go to Mars, you just stay there because, in fact, your dead body on Mars is actually more valuable than putting yourself back on a ship to come back. is in fact a more realistic solution to this problem. And indeed, Arthur C. Clarke, the famed science fiction author of 2001 and 2010, wrote even in 1967, 65, that cannibalism was going to become almost a must for long time space programs, because the body, you're not using it anymore, but the material of the body is still valuable material, which cost a lot of money to launch into space. And so you can't just bury it. That is a complete waste of material. And you would never burn it because that is a hideous waste of oxygen. So you have to come up with something else to do with it.
We have another question from Dean Rangel. He says, what fun. What does your study of the role of NASA say about the role of government in fostering scientific advance? Compare this to government's role in internet development.
Oh my goodness. Okay, so thank you, Dean Rangel, for taking me back to my general exams when I was a PhD student and making me sweat about these kinds of things. Thank you very much for that kind of thing. I'm now getting palpitations. You're absolutely right. One of the things, and this actually is where in the conclusion of the book, Kärin and I actually dwell on this kind of thing. We actually had a back and forth about actually exactly this question about whether or not solutions to global climate change, solutions to global problems could actually be solved through social interventions, through government interventions. Could they be solved through charity? Should they be solved in these kinds of ways? We went sort of backwards and forwards. And the role of the space program in dealing with something like global climate change is one of those topics. Is the space program helping? Are they hindering? Are they actually not doing anything at all? What's really going on there? I argue that in fact the space program is absolutely helping, because the space program took the whole biosphere, which we can't see because we live inside of it, so we struggle to see our own biosphere, and it put people inside a miniature biosphere where the effects of their own waste were almost immediately apparent. In fact, they were apparent within the first hour. When you're forced to wear a diaper to launch into space, it becomes pretty apparent that your waste has to come back to you somewhere. All astronauts and space programs know this kind of thing. It was also fairly obvious that when NASA had, in essence, a blank checkbook through the 1960s, the engineering solutions to these problems, which may be socially problematic, getting people to eat cupcakes made from algae that's made from feces, is really a very socially problematic thing to do. But from an engineering point of view, you can build this. One of the slides I skipped over was the last generation product, which is also at the National Air and Space Museum. It was built by McDonnell Douglas, one of the major aerospace contractors. It is a complete atmospheric recycling system. It takes all waste and simply recycles it back as water and oxygen. It deals with the lot. This thing sits on the shelf at the National Air and Space Museum because no one is really interested in that as a social problem, because we do not value waste at all. We do not value waste. Waste is valueless in our society. I like to use the idea that as not least because everyone is complaining about the price of gasoline in the United States at the moment, which of course, as an Australian, I'm laughing at the sheer cheapness of the price of gasoline in the United States. But when the price of that which comes out of the back of your car, you also are paying for the carbon dioxide that you're pumping out in the atmosphere, which at the moment you're not being charged anything for, is the same price as the gasoline that you're filling at the pump to put into your car. That is when we will have an effective solution. That is a government problem. Governments essentially need to charge the same amount for waste as they do for consumption. I would argue. Not a very popular opinion, you might imagine.
And Evan Rutstein has asked, what would you say is the most promising method or technology to deal with waste for interplanetary travel as we move forward?
So yeah, by the looks of things, actually, so the sort of the funnest example, one of the funnest, there's lots of fun examples. The funnest example we came up with, it's right at the end of the Soviet space program. They decided that the quail was the best way to go about business. The quail, it's small, you can eat basically all of it, and quail eggs are actually sterile, so they say. They keep for very long periods of time. They don't actually need to be, eggs don't need to be refrigerated. Another misnomer in the Western world. They can't be kept hot, but most eggs are kept just at room temperature. And that if you can eat and you can process, and the quail itself will eat basically everything. And so the quail then becomes an animal. So algae to quail, some other plants, presumably, probably some bugs in there as well, human, feces, back to algae, plants and bugs, quail, human, that kind of cycle. Another fun one was we should just live in water. That in fact, if we didn't breathe air, but we actually just breathed water, we breathe the oxygen out of the water, that if we just lived in an aqueous environment, a lot of this stuff would be taken care of because you could breathe and take nutrients in, which were all put in an aqueous solution. Indeed, a General Electric engineer came up with this solution. He called it the aqua hamster. He locked his daughter's hamster inside a box, which was surrounded by a fish tank with a fish in it, and the gill took or allowed oxygen to move in and kept the hamster alive. That project also didn't go anywhere, as it turns out. Not quite sure what the daughter's attitude to having a hamster locked inside an aquarium was, but I'm sure it was very fun. So these are the kinds of, what we have to innovate here is the kinds of, we have to think about our environment, we have to think about our waste in essence, completely world turned upside down ways. Again, the Soviet space program is actually probably the model. In the Soviet space program, with their closed environment, the lavatory, the toilet system itself is the front. You go in through the toilet to get to the rest, because it is through the toilet, through the waste recycling system, that the rest of the systems take place. Now imagine your house. Reconstruct your house so that everyone who comes to your house has to go to the bathroom as soon as they sit through the front door, because it is the waste, which is actually the most valuable part of having anyone over for dinner. That's the kind of sort of fun world I like to imagine.
Well, it looks like we are through all of our questions. Unless anyone else wants to chime in, I'd really like to thank everyone for coming. This was such a wonderful talk and really raises questions that I think help us to think more and better about the problems facing the world, not just in interplanetary travel. So thank you for your wonderful talk.
Thank you kindly, and thank you all for attending. I hope you have learned something. And the book is, if you need a copy of the book, there's one available in my office. I'm happy to give a copy to anybody.
Thanks very much, everyone. Have a great evening.
Thank you for watching John Jay's official YouTube channel. Stay informed, stay connected, and join the conversation. Subscribe now.